So the slides are posted like this. It's actually a good thing because I read up on it a lot, and like I feel like I really understand it. Like,
Yeah,
I
I
understand.
know. But yeah, it was really cool. Like when you first started on Facebook, yeah, make your own quizzes.
Yeah, exactly. Like doing stuff with HTML and like forcing jumps.
Yeah. And they're really emphasizing like they were trying to build up in very like one level above, but you saw a lot of freedom.
Yeah, I feel it was a good thing I listened to the slides after because the slides covered everything that all the websites like.
Yeah.
Like the Google everything is like so cool.
I know.
I was looking at examples, live examples.
I need to like actually try it out.
Yeah, you definitely should look at the actual demo page.
On like just the polymer.
Yeah, it's so Yeah, I tried accessing it.
All right. The population in this class is getting back down enough again that I can try to work on names again. Jonathan, Mina, Tamisha, Melissa. No, I want you to be Melissa. Could you be Melissa?
Like, do you even look like my ID card?
That may be the problem. Remind me.
Tiffany.
He's told me that like 3 times.
Yeah.
And I'm going to get this eventually. Tiffany. Where's the real Melissa? So there's a Jeff in this region. Jeffrey? Okay. Okay. Jimmy's. One of the Jimmys. There's 3, I think. Bill's over there. Darsh is there. That person's not in this class.
You know why? Because the reason.
All right, help me in here.
Whatever dream.
Are you Ken? What's that? Yes?
Yeah.
Yeah. Okay. Remind me.
That's why
What's your name? Yeah. I knew that. Now, those of you who I just remembered again have to answer all the questions today. First few rows, easy. Working from the back forward.
It's funny if we all just change our seats up one day.
All right, I'm gonna at some point in today's class, I'm gonna call on you for an answer, just so I can be like, Tiffany, you got it. Go.
I would just like smile.
What if we just pretend that we're these
Good morning. How's everybody doing? Get your group brainstorm thingy in? Good, good. We're going to start with a UI, hopefully, if this works. While you're watching this, be thinking model human processor. All day today, be thinking model human processor.
Today, when car makers add touchscreens to their new models, they often make things worse for the driver. Because they're cluttered with small, intangible buttons, they're harder to control and more distracting. So what if it didn't have to be this way? Let me show you how touch interfaces in cars could actually work. Instead of having a screen full of small buttons, let's make the whole thing one big control. The moment you touch the screen, the interface appears right under your fingers. It doesn't matter where exactly your fingers are. The interface just realigns with their position, and that becomes the point of reference. In order to adjust a setting, all you need to do now is drag up or down. You can do that really fast too without having to watch out to be very accurate. The reason why that works is because the interface is designed to be as forgiving as possible. Accidental sideways movements are ignored, and even moving your fingers at different speeds barely affects the outcome. That way, even with the smallest amount of precision, it still works. But how do you control different things if you don't have multiple buttons or sliders on the screen? Well, because this is a multi-touch display, you can invoke different controls by using different numbers of fingers. So with 2 fingers, you can control the volume. With 3 fingers, you control the music source. 4 fingers control temperature. And 5 fingers control airflow. And they all follow the same principle. You place your fingers anywhere on the screen and drag up or down to make the adjustment. And if you look closely, you'll see that each control has a different sensitivity. The volume, for example, changes in very small steps, because it's less important that you hit one specific number. When changing the music source, however, the interface helps you to select the right one by requiring more movement to make a change. That way, you're less likely to miss. So far, this makes 4 things you can control. But that's not enough yet. That's why this interface doesn't only react to how many fingers you use, but also to whether they're close together or far apart. Look at what happens when you spread your fingers and touch the screen. The interface goes into a different mode again and selects a different control. Instead of changing the volume like before, 2 fingers now let you scrub through your playlist. And of course, this works for 2, 3, 4, or 5 fingers. All in all, this interface gives you easy control over 8 different settings. And it does that without you having to take your eyes off the road because you're being distracted trying to hit that one small button on the screen.
All right, so what in that do you buy or not buy? Yeah.
So they say it's going to be easier because you don't have to press small buttons, but if you're not looking at the screen, I feel like you can very easily misjudge the distance between, like, my fingers are wide apart and my fingers are not so wide apart. And all of a sudden you're changing playlists and you want to change volume.
Okay, so there's this like fiddly distinction between near gestures and far gestures that I agree I'm not convinced by. Yeah.
You have to remember the number of fingers to what goes to what control.
Okay, so by its nature, right, this is a pure recall interface. Like, they don't want you looking at it, so there's absolutely no recognition to it. It's a 100% you have to remember everything about how this interface works interface. That's interesting. Back there?
There's like spatial memory with buttons. You remember where they were, you don't have to look at them. Here, it's purely visual.
Yeah, so you're deleting like all available spatial cues. True?
There doesn't show much feedback except for what's on screen, so I feel like they might have considered this to not be a video, but if there was at least like some vibrations, say like who's moved up or down a notch, I feel like that would be useful.
Yeah, so feedback is something of a challenge. You do have, on most of these cases, the audio feedback because you're like actively changing through things. You suggested haptics. Why might haptics not be a good solution in this context?
It can be a bit shocking, so you wouldn't know what people are doing.
So it might be surprising. Even worse, though, haptics just don't work in cars because the car is moving too much. Like the amount of vibration involved in haptic feedback is tiny compared to a car moving. Yep.
You can't have multiple degrees of freedom. It's like it's only up and down. Whereas if you want to control probably balance in your car from left to right or back and forth.
Yeah, so it's mapping everything to this one axis, regardless of whether or not that actually makes sense. So you lose any like relevant metaphor that you might be trying to bring to this. You lose any user expectations. All true. Anything else? Please.
It doesn't necessarily solve problems that like dials or sliders would solve out like UI.
Yeah, so it's adding new things without necessarily even really replacing all of the existing functionality. I think there's some truth to that. What's good about this? We've been critical. What's a good thing? Please.
I feel like once you get used to the control,
also just need some sort of muscle memory control. So
Okay. So at some point, maybe you can kind of push this down the stack. I've got some doubts that like you can automate this too directly, but it's plausible. Yeah.
It's really like quick, so you can just keep your eyes on the road and like reduce the amount of time it takes to get a task.
Yeah. So if you believe their claims, and there's probably a paper that we could go read, then it is better that they're kind of stealing the locus of your attention for less time, and you don't really have to stare at it, and you can just deal with that task quickly and then move on. I agree. Anything else? All right, we're going to forge ahead to the model human processor. Did everybody enjoy this reading? Wimps. This is a notoriously difficult reading. It's probably the hardest reading we'll do in this class, unless I get really bored and give you something crazy. This is one that often is painful for PhD students who are going through their prelims. So when you are a PhD student, your second year, you take a oral exam. It's a 2-hour oral exam where you stand in front of faculty and they pepper you with questions. And you have to do all this reading beforehand. It's like 100 papers or something. And model human processor is kind of notoriously one of the painful parts of that process. So now you're ready to go be a PhD student. If you're not already, congratulations. So this is one of those days where I'm going to stand here and look at my notes because this thing is just a beast. And if you have questions, we'll work our way through it and we'll try to sort this out together. All right, so first things first, why bother? Why do we want to model human performance? What's important? Yeah.
It's an easy way to think about it so that we can just communicate about it and keep it an internal way of how it works.
Okay, so it's a communications tool and a tool for summarizing kind of what we know about how people work. Yep.
If we can predict how humans may think or operate or react, it may be easier to use this than actually going out and doing task analysis.
Yeah, so there's this like magical holy grail thing here where if you could really truly model all of human performance, you wouldn't need to test on users anymore. You would just put your things up against the model, up against your simulator of what a human is, and then you're good. Okay, yeah.
I was going to say, you could also be like a validation metric where if you make changes to the design, it's not the process or turn over on. That will impact negatively positively.
Yeah, so it's a formalization that lets you kind of tighten up iterations in your design cycle so that you don't have to go out and verify how hard it is to click something every time you move pixels around in your interface. And so I think we covered all of that. That's the idea, is that basically you want to be able to get some rough idea of how people will perform before you go out and user test so that you can get the easy things right. Every few years, somebody comes along with a new model that adds features or explains more about people, and that's good. And every now and then somebody from like the AI community will come along and say like, well, we solved this whole HCI thing because we've got good models. And it's not there yet, and it won't be there yet for 50 years or something. But eventually we could be building towards like real models of human performance. So that's the goal. So this dude is like the HCI prelim diagram. Like everybody has to draw this thing at some point in their life if you're going to be an HCI PhD student. And it's just labeling all the parts in this abstraction of how people perceive and interact with their world. And so the main parts here are these quote-unquote processors, the perceptual, cognitive, and motor processors, long-term and working memory. I asked you a question on your reading response, which was basically, is this thing biologically accurate? Like, to what extent is it biologically accurate, and to what extent does it matter? Who has like an insightful thing to say on that? Yeah.
I mean, this is more of like from a biomedical perspective. The human model processor is a really, really cool cognitive model of human interaction with devices.
Mm-hmm.
But the problem is that there's a lot of things that are developed, like reflexes,
Mm-hmm.
that it can't necessarily capture. Like bivariantly associates memories with subsystems, like these
Right.
processors, you can't really find out how this is. So like learned reflexes, which is big thing with like phone in your pocket or something like that. Like,
Right.
Reflex forming. So.
Agreed?
Yeah, I think it's really inaccurate for a lot of reasons, but I also think it doesn't matter.
Yeah, I mean, that I think is the kind of fundamental thing is that, yes, this is inaccurate in many dimensions. So it's inaccurate in that it doesn't capture a lot of the nuance of how people actually operate, especially things like learning. It's inaccurate in a very literal sense in that we don't have, if I open up your brain, I can't point to, like, here's the perceptual processor and here's the arrows that go, it doesn't work that way. But it turns out that this thing is really pretty accurate for modeling human performance on kind of simple sensory motor tasks. And for that reason, it's really useful because you don't have to like invent all of basic, cognitive science every time you want to build a user interface. You have some tools against which you can validate your assumptions and validate your designs. And this is worth knowing if for no other reason than that it's extremely influential. It's just a very important piece of work in the HCI community. Cool. There's a few things I want to highlight in here just to make sure you know what we're talking about. All over the diagram, and I know it's too small to see, but there are these various deltas. What does delta represent in this thing? Do you recall? Yeah, Tiffany.
I can sort of explain it with the numbers on the right. Okay, so the two numbers in the brackets represent like a range, and then the number on the outside would be like.
Okay, so in general that's true. So we have like delta, tau, and mu here that are three different things, and you're right, we have these like ranges and means or medians or something for each of those. Anybody remember what any of those three are? Delta, mu, and tau? Yeah.
Delta's half-life.
Okay, delta is half-life, so it's associated with like memory, and the point at which you are likely to have forgotten, or 50% likely to have forgotten the thing that's stored there. Yep.
Isn't tau like cycles?
Tau is indeed cycle time, so how long it takes to do something. About mu. Truly the best of the Greek letters? Yes. Yeah, so mu is the how much can you keep kind of cached at one time part of this. Cool. So we're going to just kind of walk through this thing one step at a time. I have some things to say here, but feel free to interrupt me and ask questions. I understand this thing really well, but explaining it is always challenging, so don't hesitate to interrupt. So we're going to start at the perceptual processor. And basically, the perceptual processor is the physical store and processing center for senses, for sight, sound, touch, everything else you got going on. And it encodes, in terms of this model, which remember may or may not have anything to do with biology, it encodes directly based on the sense used. It is very selective, so people tend to, for instance, have very strong spatial memories, but very weak other types of memory. It does very interesting things in terms of what things are kind of linear time to process versus which things are quote unquote pre-attentive, the things that you don't have to kind of actively make the locus of your attention to make some sense of. It's a visual store, so you can store up to 17 letters at one time, which is good because once words start getting more than 17 letters long, they get really hard to read. We keep talking about these decay times, and here we say that generally perceptual decay is about 200 milliseconds. And so the idea here is that if you don't actively perceive, if you don't turn your locus of attention to something that your senses have perceived within 200 milliseconds or so, it's likely to be lost. And then from here, if you want to actually take some action over something that you perceive, you have to recode it and transfer it into working memory, which is a progressive process. All right, so an example of kind of how perception applies to HCI. Quick, how many 3s are in this list of numbers?
7.
No.
2.
It's more than 2.
4, 3.
I think it is 4. All right. Yes, very tricksy. Does the title count? All right, and then if I instead ask you how many 3s are here? 4. All right. And so this is the sort of thing that is pre-attentive. If, unless I lied to you, it's possible I missed one when I was like control Fing for all the 3s. But this is a very pre-attentive process. Like colors just jump out at you unless you happen to be colorblind or in other ways visually impaired. But if you have that particular perceptual system working up to snuff, then these should jump right out at you. And this is an important sort of thing to know if you're trying to build a user interface where you want to be able to kind of catch people's attention and hold it in important areas without really burning all of their cognitive cycles. And so there are a lot of these pre-attentive features of visual design. And we'll talk a little bit more about this when we actually get into our visual design lecture, which I think is going to be right after spring break, which should be fun. But I'll run through just a couple of them right now. So one that we just talked about is color. So find the outlier on the right. Should be pretty easy. So over here, you can really quickly point out the right one. And if you want to think of this in terms of like algorithms and runtime complexity, the idea here is that searching over this visual space could be like an order of n thing, where you have to check every element and say, is this the one I'm looking for? Here, we're saying that finding the like one outlier in terms of color is a kind of constant time operation. It's like an big old one operation. Yeah, I sounded like a computer scientist very briefly. All right, how about this next one? Find the outlier on the right. Okay, so there's a circle over here. How challenging did you find this one to be?
Not as easy.
Yeah, I find this to be harder than the color one, but easier than, it's certainly not, you have to scan every single item. Like it jumps out a little bit more than that, I think. And so this is another one of these pre-attentive things where, we found through experiments, and this is all very much empirically derived. People just put lots of symbols in front of people and tried to sort this out. And what you're seeing here is a battery of tests that was used by Treisman, I think, in the exploration of this issue. Apparently these are Healy's diagrams. Good to know. So anyway, the point is that this just jumps out to you. Now I'm going to give you one more. So find the outlier on the right here. Okay, so the red circle is again the outlier, and it's kind of over here. This one is much harder, and in fact is arguably not at all pre-attentive. So this is a sort of linear search required task to go through and say, all right, that's a blue circle, and I've seen a lot of blue circles before, so that's not the outlier. And I've seen lots of red squares, and then I get here and they say, oh, that's different, that's weird. But then you also, it's worth noting, even after you see that thing, you have to kind of keep checking and be like, really? Like, there's not a bunch of other red circles here somewhere, right? So point of the story is when you're doing this sort of visual design, you want to highlight most important things with pre-attentive features. Here is a table from Healy and Green on like what they consider to be the pre-attentive, also called Gestalt, features of visual design. So orientation, you can see this like wacky line is jumping out at you. Curve versus straight, that I think is my favorite because I would never think to incorporate that in the user interface, but it's true, like the straight one jumps right out at you. Differences in shape, differences in size, differences in clustering. So it turns out that the human brain really likes clustering. And so if you can cluster things in interesting ways, that's very pre-attentive. Grayscale, enclosure, that one makes my brain hurt for some reason. There's some like OCD thing in my head that doesn't like that. Convex versus concavity. That one I think is really interesting because it's an illusion. And yet we are like hardwired to believe that optical illusion so much that it works as like a pre-attentive feature. Additive things, So that one is obviously wacky. So there's the box. Juncture, that one, yeah, it's unpleasant. I think that would be, I wouldn't like that in my user interface. And then the parallelism one almost doesn't work for me. How do you guys feel about that? That doesn't jump out to me pretty attentively. Apparently I am not meant to be a geometry major. I don't think there's a geometry majors. All right. So the math behind the perceptual processor and the important things to it are that we have this notion of a cycle time. And derived from that is the quantum experience of human perception, which for the purposes of the human model processor, we're calling 100 milliseconds. And the important bit there is that anything that happens within those 100 millisecond windows tend to get kind of perceptually fused together. We tend to think of anything moving at least 10 frames per second as being contiguous. It makes sense to us that one thing is related to another. And so we take advantage of this fact in animation and in making movies and everything else where we blend together, individual frames to make it look like one contiguous thing. You'll note that most things in this world don't actually run at 10 frames per second. What's more typical? 30 or 60, which are 17 and 34 milliseconds per frame apiece. And that's basically just getting you down to the point where it's not even perceivable. So 60 frames per second is about good enough to fool most people's eyes. Some people get a little annoyed by 60 and need 70. But anyway, that's interesting from a frame rate perspective. This example I actually found really fascinating. You can do the exact same calculation to figure out how fast you can plausibly do Morse code and have the person on the other side be able to parse it because they are just literally not able to perceive it if you go any faster. So with practice, you can get Morse code down to 60 frames per second and still make it work, which is crazy. And the same thing works on causality. So if you have two stimuli that happen near each other, you basically get that 100 millisecond window to make people believe that those two things are related to each other. Why is that super, super important for HCI? Why do we care about that in the design world? Yeah.
If something's too slow, it'll seem unresponsive, so it'll seem like that's not related.
Yeah, so it's basically how long you get to, when the person taps down on the mouse, have the thing happen on the screen. You get that 30 to 100 millisecond sort of window before the user just no longer believes in it. And you see this all the time in the IoT world where if you hit the switch on a Belkin Wemo and the lights don't turn on for 600 milliseconds, it feels broken. It feels like the real world is broken, even though it's taking less than a second. You really have to get down under that 100 millisecond window. All right, here's a little demonstration. So I need a volunteer. Who's going to volunteer? Sure. All right, so you're going to tell me what you see when I play the animation. All right, what happened?
What it looked like the red ball hit the blue ball, which caused it to bounce.
Okay, anybody have an alternate explanation? And so if you run this experiment, that's basically what people say, is the red ball hit the blue ball, and then the blue ball went that way. Good for it. Yeah.
Looked like the red ball just kind of went over, slowed down.
It's because I'm bad at keynote animations. If we were doing this right. Yes. All right, so now if we do, so what most people say, the red one hit the blue one caused it to move because the red ball was hit. So the red ball is perceived to cause the blue ball to move, okay? Then if you do this one instead, you break that illusion, right? You've kind of taken the mapping out of the equation. You've taken the metaphor of physics out of the equation. And now people, when you show this to them, will no longer say the red one caused the blue one to move. They'll just say the red one moved and then the blue one moved. And what's interesting about that is that nothing is causing anything to do anything, right? There's no physics here. There's no photons hitting each other to cause the light to move. It doesn't work that way. You know, it's just poorly in Keynote told that one to move after the first one moved. And yet you really do get this like perceptual sense that those two things had something to do with one another, whether it's true or not. And so, was this in your reading? I think it was. So this is the sort of like chart of how people perceive causality. And the main takeaway here is if you can get under like left of this mean, which is in the like 70-ish millisecond window, everybody believes it. Like that's how long you have to convince effectively everyone in your population that two events were related. So when you click the mouse, if you can fire the event on the screen within 70 milliseconds, you win. If you can get it in under this like 110-ish milliseconds window, then most people will say those two things were related, but like I noticed a delay, like it was obnoxious, but yes, they were clearly related. And then it really falls off incredibly quickly. So you get into like 150 millisecond sort of territory, and people will perceive things as being two completely unrelated events. Very interesting. Any other thoughts on perception? Questions? As I said, we will have like a whole visual design seminar later this semester, so we'll catch a bunch more of that stuff then. All right, now it gets hairy. Working memory and long-term memory. So here is the chart O working memory. And the main thing to know about working memory is that to carry our computer science metaphor with us, this is sort of the register set of the human brain within the context of model human processor, with one exception being that when we think of like register architecture, usually we're talking about something fixed bit width, whereas in the human brain, like one cell of like one register may be, you know, this is what letter A looks like, and one register may be like, this is quantum physics. You know, so it's very like fluid in terms of what is stored. We have this notion, this famous result from Miller, that working memory can generally store like 7 plus or minus 2 chunks. It's not quite as true as you always hear, but pretend it's true. Where does that come at you like every day? Why is that famous? A famous result? Yep.
Is this part of the reason why phone numbers are 7?
Yeah, so it's why phone numbers were 7 digits. They decided that was like the maximum number that somebody could reliably like be told and then immediately turn around and dial. Then we all got area codes and have phone numbers from when we were 16. Now it's horribly broken. Oh well. So the important thing to keep in mind here is that this is the like, you haven't made any effort to remember this style of memory. So this only applies to like, you're doing something else and I like shout some numbers at you and then I ask you to say them back to me like while you were doing something else and you didn't rehearse them and you didn't try to memorize them. And in that context where like, if I just tell you like, remember the letter B, and then we move on with this lecture and you didn't bother like writing that down or rehearsing it, you should recall which letter that I told you up for about 73 seconds. If I were to say, remember B, Z, Q, then that might decay quite a bit faster. Like that's harder to keep in your attention for like longer than 7 to 10 seconds. And the more you're interrupted, the more your like locus is jumping between different things, the faster you are to forget these sorts of things. And so that's what this chart is all about. It's just about working memory decay times. Long-term memory is, from a computer science perspective, effectively magic. It's sort of an infinite store for long-term storage of everything you've ever learned in your life. Committing information to it is somewhat difficult. You can, you accidentally long-term store lots of things every day, but purposefully shoving things into long-term storage is a process, and it's a process that you kind of have to learn how to do. So studying is not something that necessarily comes natural to everybody. It's something that is an acquired skill. Super fast read times, although not like computer fast, it's worth noting, but like on human scale, very fast read times, and then rather expensive writes. So like moving things out of working memory and into like really long-term memory is a challenge. And part of the way that we do it in real life is via rehearsal. So kind of thinking about something over and over again, putting it into some sort of more proper context. And that is the key to acquisition time for retrieval. So if you can kind of remember where you were when you learned something, or why you learned it, or what other things are related to it in your mind, it's much easier to retrieve things from working memory. I think the most interesting case of this, watching this in action, is watching really good Jeopardy players, because really good Jeopardy players are like word association maniacs, and they're very good at pulling things out of their brain based just on like contextual clues within the actual prompt. Very interesting. Yeah, so my notes remind me to tell you that if you think about one particular event in your life, so think about like sometime a sports team you care about did really well, or your first kiss, or something, your prom dance, I don't know, kids these days, whatever you do. You might remember suddenly lots of other things like, oh yeah, Jimmy, what the hell ever happened to Jimmy? Sorts of things. And lots of things can come flooding back to you just by like putting yourself in the right context. So very interesting. Moving on. All right, we're gonna do the cognitive processor next. What's this one all about? Yeah.
Like a summary of information which you get from your perceptual processor.
Yeah, so it's taking the information from the perceptual processor and kind of working with those percepts and things you already know. So like things that you have in memory in order to make some sort of conclusions. So this is where we get like really super hand wavy about the biology, because one, it super doesn't matter to us. And two, it sounds really complicated. So screw that. We're just going to say that it's sort of like a computer because we understand computers. And we'll say that as it's sort of like a computer, it has a cycle time of about 70 milliseconds, though that can be modulated by like how well you know how to do something. So we are trained as like individuals in our society to be good at like matching and recognizing digits, or matching colors, or matching shapes. And so as we kind of hone those skills, those become kind of faster cycles. The most important thing here to remember is that the cognitive processor in our conceptualization of it is really fundamentally serial. And so if you think of yourself as like a good multitasker, you're not really a good multitasker. You're a good context switcher. Like that's what makes one person a good multitasker or not, is how kind of quickly can you move your locus of attention between different things without scrambling your working memory. Basically, that's fundamentally what a multitasker is. But you really don't kind of attend to more than one thing at a time. The brain just doesn't quite work that way. And if you're interested in this topic, like really go read The Humane Interface by Jeff Raskin. If you're going to buy one HCI book, that's the one to buy. I've said it several times in this class, but it's my favorite book. So go read it. A famous example of this, you'll note that all famous examples of HCI problems are airplanes crashing. And here's another one. This is from December of 1972. And what happened was like the plane was in trouble and it was going down and losing altitude, and the landing gear wasn't doing what it was supposed to do. And there's this blinking light that says like the landing gear is broken. Okay. And all the pilots, and you can listen, you can go online and find the recordings if you feel really grim, of the like cockpit recorder, black boxy sort of recordings. And they're talking about this flashing light. Like, why is this light flashing? What's up with that flashing light? I wish that light weren't flashing, sort of things. And in the meantime, there's like sirens and like, woo, 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 engine failed, crash, sorts of things in the background. And they're like, but what's up with this light? Like, That's weird. And they never noticed. Like, they never noticed that they were losing altitude and they were about to plow into the ground because they were so attentive to this stupid blinking light that really had nothing to do with the fact that they were crashing. And then they went down in the Everglades and everybody died, and don't do that. Questions on cognitive processor? All right, God help us, we're gonna walk through an example here. So here is, we are going to do, what are we doing? Oh no, I lied. We're gonna work through an example in a minute. Sorry, we're doing the motor processor first. What's the motor processor do? This is an easy one. Somebody new. Yes? Yeah, so it takes the like kind of intention to act on the world and turns that into like, how do I actually act against the world? And so it receives input from the cognitive processor and it executes what we're calling motor programs. And the key thing to get here is that while the cycle time of this thing is whatever the chart says it is, 70 milliseconds, 30 to 100 on average, that doesn't mean that you can physically only do one thing every 70 milliseconds. What it means is that you can kind of only execute one new program, one little like finger macro, so to speak, every 70 milliseconds. And so where a pianist can get up to like 16 finger movements per second without any problem, it's because those are programmed. And so when we talk about like muscle memory, this is kind of a formalization of that notion where you know just really deeply how to do a sequence. And instead of saying like move up one, move right a bunch, hit down, 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 you are instead sending the like type the letter G command to your hand. Really interesting. It's how we learn to touch type. It's how we learn to play instruments. It's how we learn to play sports and throw darts and whatever else you can imagine that kind of involves fine motor control is only possible because of this like programming your muscles to do certain things. And again, that has literally like no biological meaning, but in our model, go with it. This is kind of a cool example. So if you draw two parallel lines and you ask somebody to just go as fast as they can between the two lines, they can draw like 70 of these things in 5 seconds. So they can just go choo. But if you tell them like, all right, now this time I want you to be really careful not to go outside the lines, like make sure you hit the line exactly every time, then suddenly, while you can get a bunch more lines, you end up seeing that they cluster into like these groups of misses. And those groups of misses change at that like 70 millisecond sort of window. So people realize that they're going too far and can fix it. And they can do a bunch at the like new programmed width, but they can't actually correct faster than that 70 millisecond window because there's this sort of point of no return for muscle action. Yep.
So once you hit the perfect width,
what
causes you to lose control and again go back?
Presumably just that you're not that good at doing this. I imagine if you practiced it, you could get really good, but.
So the 70 millisecond rule doesn't really apply to when you are hitting a target?
It would, but remember that you still have to perceive that like this is good and then perceive like I need to keep going. And so you just start to drift. It's the same thing where like if you close your eyes and try to walk in a straight line, it's really hard because people just don't work that way. People need feedback. It's one of my favorite Mythbusters episodes, if you've never seen it, where they like blindfold themselves and try to walk in straight lines across fields. And they end up like walking in big spirals all over the place. Really interesting. Cool, that's good. Any other thoughts on this? Great. Okay, so now we're gonna work through an example. So this example is in the reading and I just wanna make sure that everybody kind of gets it. So the question here is, what is the process your brain goes through if I say, hit the space bar when the letter A appears on the screen? And so first thing that happens is the letter A or alpha or whatever I put on there shows up on the screen. What happens next? Yeah.
Basically, when you perceive it, when you process that seeing a letter.
Mhm.
The brain tells you exactly what letter that is, you validate that, and then the brain basically tells you muscle.
All right, so next up we get like, it shows up in your like working memory because there it is, you perceived it. And now your like perceptual processor can work over it a little bit and say like, is this a thing that has some meaning to me? And you can say yes. And then your cognitive processor can say, all right, I know what an alpha is, and I know this thing I just saw, like, are these things the same thing? Yes. And then it can move along and say, okay, motor processor, I want you to go and hit the button. And then it goes and hits the button. And if you just add up all those times, you get some notion of like what performance should look like on that experiment. And so you can go home and try this. You could write a quick JavaScript application to like wail on the keyboard when the right character appears. And you'll see that if you do this, you can get better at it. Like there's some improvement possible. But in general, it just sort of follows the rules. Yep.
Understanding or interpreting the alpha as alpha
Mhm.
is the cognitive processor or
I'm going to say cognitive processor. That seems like something the cognitive processor should do.
and then so what is the other processor, the perceptual processor work on?
The perceptual processor, I think, is just like chunking that thing. So instead of it being just like, here's 300 pixels and some of them are red, it's doing the work of saying this thing is an alpha, you know, or this thing, not even that, but this thing is a unit that has this shape. So it's kind of like vectorizing the raster image, so to speak. And then your cognitive processor is coming in and saying like, okay, but not, and I have like a vector match between these two things that I already knew. Cool? Okay. It's worth pointing out here that like the scale we're talking about is tiny, and people have made models for all sorts of different scales. So this is Newell's human interactions loop model, and it starts all the way out at this like affect social change and like, you know, convince other people that you're right sort of scale, and then works its way all the way down to the motor loop. And so where this might be 10 years, we're currently talking about the like 70 milliseconds sort of windows. And so just keep in mind that there's this whole range of ways that this is applicable. All right, and then principles of operation: respect the limits of human performance, don't make the user remember more than they can or for longer than they can, and bear in mind that, you know, on every cycle, you're competing for attention with kind of everything else that's going on in the room and in the person's life. Cool? All right, we're gonna move much more quickly, hopefully, through memory. I'm gonna skip this. Everybody's seen this before. There's this famous experiment where if you have people say the colors, that's much easier than if you have them say the colors there. And the reason for that is that it's difficult to pull things out of memory when you have kind of conflicting parts of the brain wanting to access memory at the same time. And so there's this thing called stage theory of memory. And it basically just says that you have some very, very small sensory image store that decays extremely quickly. Some things move into working memory. Some of those things decay out of working memory just as a matter of how the brain works. Some of them get displaced by new stuff coming in from sensory memory. And then if you want to move something from working memory to long-term memory, you have to maintain it and like actively reverse it. Then when you want to pull something back out, you have to pull like one chunk out. And then things sometimes just don't come out quite right when you're trying to remember something. We don't kind of in model human processor and in like HCI, CogSci land have a model of decay within long-term memory. Like we sort of assume that people never actually completely forget anything. But we do very much have a model of interference where remembering one thing is difficult because you have something related to it that's just getting in the way. So from our perspective, just remember that working memory is small and that to really long-term remember something, it involves rote repetition and, you know, maintenance. Real elaboration, which is how you kind of like build onto your existing mental model of how the world works, is how like real serious long-term memories are built. And so if you can do something to tell a story or attach meaning or attach space or time or smell to a memory, it becomes much easier to actually remember it. So there's all this work out there on like memory palaces and different ways to remember facts. Interesting stuff. And so the main reasons that we don't remember things are, one, that we've never bothered storing them. It's a failure of encoding. Two, that it's just gone. Or three, that we have some sort of retrieval failure. And then our main model for forgetting is actually just interference, where one thing that you learned reduces your ability to remember another one. And that can be either proactive or retroactive, where either like old things interfere with new learning or new things interfere with things you used to know. Thoughts, questions, those models? Okay, we're going to take a brief break to talk about class things. So your brainstorm is in. Everybody do okay on that? I'm hoping for you guys to get feedback from GSIs pretty quickly on whether your idea is like sane. You're not at all committed to this idea like permanently, but the hope is that you'll be committing to a user group really quickly, because you do kind of have to dive into this next bit of like contextual inquiry really quite quickly. Heuristic evaluation assignment is out. It's due next Tuesday. This should be pretty quick. So take a couple hours and knock this out. But you have to just choose a smartphone application and then do a heuristic evaluation of it. It's just a way for us to get you kind of one more individual assignment before you get too deep into group work. So do that as soon as you can. And then the big one is the contextual inquiry task analysis competitive analysis thing, which is due next Friday. We'll talk a lot more about that next week, but really start on this soon, because you have to find real participants. And I really, really care a lot that you find target users that are representative of who your actual target users would be. So I really don't want you interviewing people that are irrelevant to like your product. Yep.
So you say no CS160 students. What
True.
about college students? Because I know in previous assignments it said no college students.
If college students are your target market, try to get more specific. So like it's rare that like your product is going to be for everybody, but if your product is for college students that ride BART and have a bike, then sure, like go talk to college students that ride BART and have a bike. Yep.
So our target user group is they're people with debilitating illness. So we can't really get access to who has this and who doesn't.
Right.
So how can we do contextual inquiry to the same capacity as say somebody who needs to talk to?
Yeah, that's tough. Talk to me in office hours about it, and maybe we can come up with a coherent plan. But if you have a relationship with, a hospital, or it's tough. So my suggestion would be to, if you can't come up with anything better, talk to healthcare providers, people that would work with the sorts of people that would be your target users. That's maybe the best proxy you can get. That will be a challenge for you throughout the semester, though. Anything else? All right, next week we're going to do input devices on Tuesday and prototyping on Thursday. I will post readings tonight, hopefully, and they will be at least marginally less painful than model human processor. The input devices reading is a little dense. I had the 260A students do one of those readings for today, I think, maybe. Is that all right? Cool. All right, so to take a break from model human processor, we are going to do my first in a series of what I'm calling the Hall of Interesting for individual programming assignment 1. And these are solutions to IPA 1 that I think are interesting, and that's all. Like, I'm not saying that they got the best grades or that they did anything even necessarily well. I just think they are representative of interesting solutions. For most of these, I'm going to mute the sound and spare you the embarrassment of having to talk to everybody. 2 of you do not get that courtesy. All right, so here's a solution that I thought was interesting. So lots of people did kind of slider and radio button based solutions. And I think this was my favorite of these slider and radio button based solutions. So it's just a slider up at the top to set the temperature, and then a bunch of radios on the left to pick the input, and radios on the right to pick the output. And then the conversion happens up here, and then all the other conversions also happen down there at the same time. Like there's a lot going on, but I think I like it. Okay. Contestant number 2 is the only app we got that bothered thinking about monetization. I have a certain appreciation of that. So they left room for, this is where you put in your like Google AdSense mobile ad aware ad. Good on you. Yes, and also Katy Perry themed. Not every app was Katy Perry themed. The next kind of class of these things were text box based. And so this, I think, was my favorite text box based app. Very clean. I like the colors. Resizes well. It has its issues though, which is that if this person ever gets around to typing, some of you like could not find math.round and decided to give us like 7 million significant digits. Math.round is your friend. So that's a cool one. Great. This one, I just have a still image up because I couldn't figure out how to download videos from Vimeo. But this is the only person I saw that bothered busting out the scientific notation once temperatures got really high. So when you get into the like hundreds of thousands of degrees Kelvin, which by the way is really hot, you get into conversions into scientific notation. Very fancy, and then actually should look at the code and see how that worked. Probably there's a JavaScript function that does that. This was my favorite like wacky input one. So this was like blue on top and red on the bottom, and then you can drag anywhere on the screen to like change the proportion of those two things. Thought that was a good solution. And they found math.round. Very good. I almost went through and took a point off from anybody that let you go below 0 Kelvin just because it really annoyed me, but the GSIs wouldn't let me do it. It's absolute 0. It's really cold. You don't need your temperature conversion app to go below absolute 0. And then this may be my favorite of the apps, actually. I liked a lot of them, though, I will say. But this one was interesting. So change temperature scale by clicking in the middle, and then change temperature by clicking on the top or bottom, and incrementally change the background color, which is non-trivial to do, actually. Like finding a reasonable mapping between number and color is not super, super easy. So good on you, whoever that was. All right, 2 of you don't get the courtesy of having the sound muted. Sorry. So these 2 were my favorites from motivation perspectives, so gave me good explanations of why they were building their app.
When I was in high school, my dad would drive me to school every morning. He always had the temperature gauge set to Celsius in his car, so I made it a habit to calculate what the temperature was in Fahrenheit. Even though it would take me less than a minute to do the calculations, because I did this every day for about 2 years, the time I wasted converting these temperatures is about 6 hours. What if I told you that you don't have to waste 6 hours like I did to convert temperatures? What if you could even calculate the temperature in Kelvin at the same time? Introducing the KFC converter. Simply tap one of the 3 white boxes, put in the temperature you want to convert, and watch as the other temperatures are automatically updated. You can even convert from a different temperature scale to the one you already input. So if I want to find out what 40 degrees Celsius is like in Fahrenheit, I simply have to input it in the correct white box, and it'll update the other values for me. The KFC app even considers your fear of trailing floats by only calculating values to the nearest 2 decimal places. As a bonus, This app acts as an appetite stimulant for when you're craving overpriced fried chicken. Please do not KFC converter while driving or walking on Sprout.
Okay, a favorite of mine, very good. Gives a clear story. And so while this application is technically no more sophisticated than many of the like text box entry versions, I quite liked the video and I quite believed the case being made. Then we get to my favorite video.
Meet Paul. Paul is an alien from outer space who's starting a new life on Earth. Paul's species communicates using changes in temperature, but there's a problem. Paul only speaks in Kelvin, and the other Earthlings around him, they only speak Celsius or Fahrenheit. What's a poor alien to do? Luckily, Paul has a temperature translator app, which allows him to convert temperatures. All he has to do is input a number in the input temperature field, and then choose which units to convert to and from. The answer is displayed at the bottom. He can convert from and to Celsius, Fahrenheit, Kelvin, and that one that I can't pronounce. It even works with negative numbers. Paul gets confused with Earth numerals sometimes and types in letters by accident, but this doesn't do anything, so there's no way to misuse this app. Finally, there's a way for Paul to communicate with Earthlings, and now he is so happy to be surrounded by his Earth friends. The end.
So if I were grading the assignments, that would have gotten all the points. I love that. All right, so that is my Hall of Interesting for IPA 1. I'll do the same thing for IPA 2. Next time we have a lecture topic I don't like. All right, moving on. Decision making and learning. So in your reading, you did mostly model human processor. It turns out there's lots of these models that predict human performance. And I just want to toss a few more of them at you just for fun. Who has ever walked into a store that looks something like this and then walked back out without purchasing anything? So we have this notion in cognitive psychology of kind of choice paralysis, feeling overwhelmed by the number of choices that are made available to you, and then not being able to turn those choices into a concrete action, not being able to go out and do something. So we have a cog-sci model for this called Hicks' Law that basically states that the cost, that is the time of making a decision between n choices, scales logarithmically with the number of choices. So if you have n choices, you have to process those in log time, even if there's an obviously superior choice. So you have to kind of work your way through all of them. Good news is that it scales in log time, not something worse. But can anybody tell me why n plus 1? I know this is a random question, but so if you have n choices to choose between, why does it scale log of n plus 1? What's that? Well, log 0 is bullshit, so you better put some constant in there. Yeah, so it's accounting for the just walk away, screw you store, I'm out option. So this is one of the bajillion D models in cognitive science that follow logarithmic sort of distributions. The other class of classical models from cog-sci are power law sort of distributions. And so it turns out that everything that people do in life works kind of on a power law. So what this is telling you is that in the power law of practice, the time it takes you to do a task on the nth time that you have done it follows a power law. So it's T of n is the base time to the negative a, negative alpha, I guess it's trying to be alpha, plus c, where it turns out alpha is basically 0.4, and c is a limiting constant to account for the fact that no matter how many times you practice something, you'll never be infinitely fast at it. So if this is, I'll test your maths. If this is the equation, what does it look like? What if I had to draw the graph of how long it takes? So this is time over practice. What does that graph look like? Yeah, so it's an exponential decay sort of deal, so it looks kind of like that, something like that. And indeed, it looks something like that. And this thing is incredibly predictive of how well people perform on sensory motor sort of tasks. So if you let people practice at things, you expect to see this sort of distribution. There are a number of reasons this is important to HCI, but can you come up off the top of your head one really important reason that like an academic HCI sort of person would care about power law of practice? It's an experimental design thing. I'll give you that hint. It's really easy to end up with bad results when you're doing user studies if you really are trying to measure these sort of finicky like performance on sensory motor tasks, because you have to be really careful about whether or not you let the person practice. And if you do let them practice like using interface A, you have to let them practice using interface B the exact same number of times. You have to really carefully control those trials, or else you end up with like lots of weird nonsense in your data. And so you'll see people present data and like they're claiming some real result, and then like a power curve pops out of it, and you're like, I think you cheated somehow. So the main point though is that you get faster the more times you do something. This applies really only to skilled sensory motor sort of behavior. It does not apply to like learning. It doesn't apply to more cognitive, like memory-oriented tasks. And it also, really importantly, doesn't apply necessarily to improving quality. So while you will get faster at the task, you may or may not be getting better at them. It's kind of an unrelated axis. Yep.
Is the multiplication table an example of learning that gets faster and more?
Yes. Yeah, I mean, I'm not claiming that these things don't get faster. They just don't follow that particular distribution necessarily. Although I wouldn't actually be shocked if that one did. Somebody go find some second graders and let's find out. I know how we can run a test. Yeah, I don't know exactly how that sort of thing works. So we have this notion of stages of skill acquisition. So imagine that you're trying to learn how to use a manual transmission. I will have to imagine with you, sadly. And when you start, it's this like, all right, let off the accelerator, put the clutch down, move the shift lever, move the shift lever, move the shift lever, do the clutch, do the accelerator. It's like these completely atomic steps where you have to really actively think about each one. And indeed, you can see that in the way you talk about it. So like if somebody else was teaching you how to drive a manual transmission, this is the way they would describe it. You would verbally represent it in that sort of same way that a person actually thinks about it. And then you would start to chunk these things. So you would start thinking about it eventually in terms of like, all right, now I need to move my foot over here, and then I need to shift, and then I need to move my foot back. And then eventually, when you get kind of used to this thing, it's just like, all right, now I need to shift. And so over time, the kind of chunks that you build of how you interface with your environment get larger and larger, get more and more automated, get faster and faster, to the point, in fact, that it can become difficult for somebody to teach these sorts of skills. So when somebody is trying to teach somebody to drive a manual transmission, the first thing they say is like, well, you just shift, like shift, and then you're done. And you see the same thing in like cooking, and you see the same thing in lots of these kind of like skill-oriented tasks that involve a lot of tacit knowledge and are rather difficult to describe to somebody. It's like, yeah, just go mince the onion, like do it. Come back when you're done. Make sense? All right, one more big cognitive model is Fitts law. Who's read anything about Fitts law? Was this in the model human processor reading? I know it was in the 260A reading. Fitts law, super, super famous. Probably the like most well-known thing about HCI to people that aren't in HCI, actually. If you go out and you're like a UX sort of practitioner, everybody wants to talk to you about Fitts law. Do you know about Fitts law? Then I want to punch them. but it's much better than them asking me to draw them an icon, which is the other thing you get. All right, so Fitts law basically is a description. And you want to stop the mouse cursor anywhere in this blue bar, okay? That is the sort of task that Fitts law models and tells you all about, what human performance on that task should look like. So the key things to keep in mind here is that this is using the whole model human processor cycle, because the way people actually draw lines in real life, if you're trying to do this task, you don't just like look at this and say, okay, I need to get from here to here, and so I'm going to draw a line this big. What you actually do is you put your pen down and you say, all right, I'm going to go a little while, and then I'm going to check. Like, I'm going to see how I'm doing on trying to hit that target. And as I get closer to the target, I'm going to move slower and slower, even if it's only microscopically, and more frequently check in to see if I'm like arriving at the place that I was supposed to arrive at. So I draw the line, and I made it. Hooray, I passed Fitts law. And anyway, so we have a formula that describes how that works. Time it takes is alpha plus beta times this logarithmic term. A and B are constants that are empirically derived. And what's interesting about A and B is that they are, one of them is dependent on the person, and one of them is dependent on the input mechanism. So there are arbitrary input mechanisms in this world, and we're going to talk a lot about that next week. But some of them are much better at aiming tasks than others. So for instance, like trackballs are kind of notoriously difficult to do aiming tasks with, whereas like mice are really super easy to do aiming tasks with. And so one of those constants, I think it's B, is determined by the ease of use of the actual input device. This D here is distance, S is the size of the target in proportion to the angle at which you're approaching it. So it's like the slice of the target that's relevant to you. And then this term here, the log base 2 of D over S plus 1, is called the index of difficulty. And so you'll always hear when people talk about pointing and aiming tasks, like what is the index of difficulty of that particular task? And so this models well-rehearsed selection tasks. The time naturally increases as the distance to the target increases, but the time also increases as the size gets smaller, or decreases as the size of the target increases. And so the point of these things is that something like this, these two like degrees of difficulty, indexes of difficulty, are equivalent. So if you start really close to a small target or start really far away from a large target, these terms will all balance out, and these end up being exactly the same sort of difficulty. Conversely, you have to consider both. So here we have roughly the same distance but a much bigger target, and so this task is much easier. And then over here we have the same size target but more distance, and so this task is much harder. You can test this, and people do, and this is like a canonical thing to make students do, but I'm not doing it this semester because it doesn't sound like fun. But if you go out and you get like 5 people to do these sort of like aiming tasks, you'll find that the data like looks like this. So this is the index of difficulty, and this is the time it takes to actually do the movement. And so this is a logarithmic scale, and it ends up on the logarithmic scale being super, super linear. And this is one of those reasons that like Fitts law is so well known, is that when you do experiments with like humans, real people, the data never looks like this. Like you can't find anything else in the world where you get this like incredibly beautiful linear line out of your data. And yet Fitts law always gives it to you. And so it's well known just because it's incredibly predictable. Thank you, pointing tasks, for being incredibly predictable. There's a classic HCI question here, which is, so I've just told you that this describes motion along like a single axis, and you're trying to hit a target, and you base the size of it on like what piece of the target you're going to hit. How would you go about extending this law to two-dimensional spaces? So imagine that, like, instead of being a slice, your target was like a box, and you started over here instead of like always being directly square to it. How would you go about Fitz-lawing that space? Yep.
Maybe you could establish like a line that's like the best case possible scenario and see how people track across that line.
Okay, so you could like find this space and you could say, all right, well, this is probably, you know, the slice that you're aiming at, and so I'll just reduce it to like the one-dimensional case.
You can maybe track the error across from that line.
Yeah, so that's one way to do it. Other ways you could do it? Yep.
Maybe have walls along the way you can't hit.
Okay, so you could do like an experimental design thing where you like shock the person if they go outside those bounds. That would be fun. I like experiments where you can electrocute people. We're going to get to experimental design paper at some point, and then I'll make you read a paper about why you shouldn't electrocute people. So that was a joke. Go read about the Milgram experiment. Great fun. Some cruel psychology researchers out in the world. How else would you do it? Come on, clever people. So it turns out that this would be really accurate, but it's really hard to compute in the general case. So that's why people don't use it. So to be clear, we're talking about like moving from a point and hitting some target someplace. How would you calculate the expected performance on hitting that target? Now I have you Fits in the Tantrum song stuck in my head. I blame my slides. Anything? I can sit here for 5 more minutes and you can't stop me, so somebody has to say something. Yep.
Would you kind of find its center of mass and then reshape it so that you have the same effective initial?
Okay, so that would be a way to like make a user interface better based on what you know about Fitts law. Anyway, this is now no longer interesting, but basically what you do in real life is it turns out that if you just take the shorter dimension, so you have like a short dimension and a long dimension, Fitts law holds for these targets if you take this to be D and you take the shorter dimension to be S in your index of difficulty. So basically you can always just treat it as if it were like as hard as it could possibly be. Famous HCI question that was solved famously in the 90s. Thoughts, questions, modeling human performance? So where we're going with this, just so you have a little lay of the land, is next week we'll talk about input devices, I think on Tuesday's lecture. And I will talk at some great length about like how we use what we know about human performance and Fitts law and all these things in order to make better input devices and in order to make better user interfaces that work around those input devices. Anything else? Go do your heuristic evaluation before it's too late. Like, don't let it get in the way of your group assignment. See you next week.
Yeah, I was just thinking, wow.